I'm not going to worry about that for now. All right, so it should be on slide 30 for you guys. Um, okay, so have you ever spent hours rereading your biology notes, highlighting every single sentence until the page looks like a neon yellow glow stick, only to blank out during the actual exam? So it is a very infuriating feeling, but understanding why that happens and how to fix it is precisely why we rely on the scientific method rather than just random guessing. Psychology is not about reading minds or making wild assumptions. It's more a rigorous science driven by four fundamental goals. So when psychologists observe any human behavior, they're trying to tackle four key questions in order. First, description, what is happening. Second, prediction, when will it happen again. Third is control, what causes it to happen and can we manipulate it. And fourth, explanation, why does all of that happen in the first place? So to systematically answer these four questions without falling victim to bad logic, researchers follow the scientific method, and it all begins with step number one, formulating a hypothesis or a theory. So in everyday conversation, people often use the word theory to mean a random hunch, like believing your gaming console is intentionally crashing just to ruin your winning streak. But in the scientific world, a theory is a well-sustained explanation of how a phenomenon works, built from interconnected ideas that explain existing data and make testable predictions about future outcomes. So think of a theory like a strategy guide or a master build in Elden Ring, as it takes all the available information you have about the game mechanics and maps out the absolute best way to navigate the environment successfully. So however, you cannot just invent a scientific theory out of thin air while sitting on your couch. Before formulating a solid theory, researchers have to do their homework by conducting a literature review, diving into academic databases like Google Scholar, EBSCOhost, or JSTOR, or whatever it happens to be, for things that are related to their topics like study habits or retention. And by reviewing peer-reviewed articles, scientists can see what prior researchers have actually already discovered. Maybe your question has already been answered and you just didn't know it because it's not common knowledge, and so you dig and you find that out. Well, then you don't have to do an experiment, or you have to change your question, or whatever it happens to be. So, for instance, after reading literature review on memory, a researcher might formulate the theory that students retain information significantly better through active self-quizzing than through passive rereading. This foundational theory then synthesizes past observations into a coherent model, setting up the ultimate framework for researchers to design an experiment, test their ideas, and crack the code of the human mind. Maybe you've crafted a super specific fan theory about how your favorite streaming show is going to end down to the exact dialogue in the season finale, just so that you could prove to your group chat that you predicted the future. All right? So if you've ever put your reputation on the line with this precise of a prediction, like maybe predicting the ending of Stranger Things, and then having to tuck your tail between your legs whenever you're wrong or whatever, with a precise prediction like that, you've basically executed step two of the scientific method, which is formulating that hypothesis. All right. So once a psychologist establishes an overarching theory, they cannot just stop there and celebrate. A theory is the massive big picture blueprint, like claiming that a specific strategy build in Genshin Impact or League of Legends yields the highest damage output in the game. But to actually prove that this big idea works to the rest of the scientific community, you have to narrow it down to a hypothesis being that specific testable prediction about what will happen under exact conditions if your overall theory is actually correct. Think of it like the grand overarching narrative of your theory and zooming in on one isolated measurable battle for you to test out. A single theory can actually spawn dozens of different hypotheses depending on what specific variables you choose to measure. For instance, let's go ahead and stick with memory theory since we've mentioned it. The idea that active self-quizzing leads to better learning than passive rereading. So to turn that grand idea into a testable hypothesis, we have to make it concrete and measurable. So a researcher might say something like, students who complete 3 active self-quizzing sessions will score at least 10% higher on a multiple choice exam than students who reread the textbook chapter 3 times. Notice how the statement avoids vague, fuzzy languages like students will feel more confident or students will learn better. Right? It lays out a very clear, very measurable prediction with a direct cause and effect relationship that can be tested in a laboratory. The level of precision is critical because it targets psychology's ultimate goals of control and explanation. And by controlling the exact study method students use, researchers can then develop an explanation whether active retrieval directly drives higher test performance or not. And it transforms that broad scientific hunch into a sharp, clear prediction that is ready to be put to the test in the real world. So, have you ever tried to figure out why your favorite video game crashes at the exact same moment in the boss fight? All right, this is really probably much more of a problem with older games. So, just a side story. Specifically, I remember this happening a lot in the Tekken video game series, where you get to the big finale, and then for some reason, like the console couldn't handle it or something. But anyway, so first you might describe that problem to your friends, then you might try to predict whether lowering your graphics settings will stop it, and finally you actually change one setting at a time to prove what caused the glitch in the first place. So when psychologists reach step 3 of the scientific method, they do exactly the same thing. They pick a research method to put their hypothesis to the test. Depending on their goal, researchers choose from 3 primary paths. If they simply want to observe and document the behavior, like asking what study habits do high schoolers already use. They use a descriptive method if they want to predict whether 2 things change together, like asking is there a link between screen time and test scores. They use a correlational method. But if they want to prove definitive cause and effect, like proving whether study strategy A causes better grades than study strategy B, they must use an experimental method. So since our goal is to prove whether active self-quizzing directly causes better test scores in our hypothetical situation here, we have to run a controlled experiment, and in any experiment, researchers work with variables, which are factors that can be changed or measured. So the factor we intentionally manipulate here is called the independent variable. All right, so the independent variable is the changing variable. We manipulate it, right? It's in our hands, so to speak. So in this case, the specific study technique assigned to students where one group relies on repeatedly reading while the other uses flashcard quizzes. The factor we measure to see if our manipulation had any real impact is the dependent variable. It is dependent on the independent variable that we are manipulating. All right. So that's the final exam scores. So to keep the experiment fair and avoid running into unfair advantage glitches, scientists use random assignment. This means every participant has an equal chance of being placed into either the reading group or the quizzing group. So because random assignment balances our background differences between 2 groups, researchers can confidently conclude that any final jump in exam scores was actually caused by the self-quizzing method rather than sheer luck or baseline intelligence. So once an experiment concludes, you are left with a massive amount of raw data, scores, times, or survey answers, and that means almost nothing until you organize it. And the very first task in data analyzing is to summarize the data into clean, understandable metrics. So in an experiment comparing study techniques, for instance, you would calculate descriptive statistics like the mean or average exam score for the group that used passive repeated reading versus the average score for the group that used active flashcard quizzing. So summarizing raw data compresses hundreds of individual student test scores into 2 very clear numbers for us. In this, we simply see that the quizzing group averaged an 88%, while the reading group averaged an 81%. And it's not enough to claim victory. Next, researchers have to determine if that difference represents a statistically significant effect. And in scientific terms, this means that the observed difference between groups is large enough that it is extremely likely to have occurred, unlikely to have occurred rather, by random chance alone. Think of it like a critical hit rate in a role-playing game. If your damage output spikes once, it might be a random fluke, but if it consistently hits a higher number across hundreds of battles, you know your character build is genuinely overpowered. If the statistical test proves the higher scores in the quizzing group were not just a random fluke, the results officially support your hypothesis that active practice causes better learning. Now here's the most crucial rule in all of scientific research. You can never, ever alter your original hypothesis after you see the results. Imagine playing a game of darts, throwing a dart totally off target into a blank wall, and then drawing the bullseye around where you hit. That is cheating. right? In case it's not clear. So instead, changing your hypothesis after looking at the data is a practice known as harking, or hypothesizing after results are known. Right? It's considered a massive ethical violation, and it does happen more often probably than what you're aware of in studies where people are trying to, especially anything that is being used in the realm of politics. I would be wary of psychological studies that are used in politics, especially because it happens a lot with those particular ones, and then they're proven wrong later, and then by that time, it's usually too late. People are going to believe what they believe. All right, step 5 is reporting your results to the scientific community, ensuring that all data and interpretations are included. All right, so this means total transparency. You have to share all of the data, the messy parts, the unexpected outcomes that completely contradict your original predictions. Intentionally hiding bad results and only showcasing data that supports your own theory is an unethical practice known as cherry picking. All right, so this is another thing that why I say in politics in particular, be very careful, because there is a lot of cherry picking from different scientific papers that goes on. All right, so you have to take the whole thing, you have to see the whole thing, right, in order to come to the proper conclusions. So this is then reported. You might, depending on what this is for, if it's for grad school or something, or you're earning your PhD or something like that, you may have to present it in front of your peers. It may be something that you're paid to do, and so you're going to present it at conferences and stuff like that, and do presentations and that kind of thing. That goes over everything that you have done. More than likely, you're probably publishing your study in some sort of scientific journal, whether that's the American Psychological Association's journal or Psychology Today or whatever it happens to be for the subject we're talking about. And then those results need to be able to be easily replicated. All right, so the scientific community does not officially say, like, put support behind anything until it has been replicated on multiple occasions. So, and as a result of that, no single study really provides definitive answers. Additional research with more diverse participants and in various contexts enhances the confidence in the results of validity and generalizability as well, where you apply everything to the larger population. But again, psychology is, sometimes it takes years for someone to come along with a question that pokes holes in the research that everyone thought was solid for a long time. I mean, we still have a lot of people who follow like 80% of Freudian theories, even though it's been disproven by the scientific community, the psychologists, the APA, for decades upon decades now. And I mean, I have talked to people who are Freudians, like they really believe what the guy was saying was great, right? And that's all well and good, but you have to remember his stuff was disproven and probably had something to do with all the crack that he was smoking, right? Just saying, he had a little bit of a drug problem. So why should we follow the scientific methodology in psychology? It's quite simply, it's the most solid way to come to a conclusion that is valid. Okay? It's the best way to have evidence to support your conclusions. It's a systematic and repeatable process. It helps to identify cause and effect. It's just proven over, well over 100 years now that it's the best way to go about things. All right, so different types of research methods that we have. So descriptive methods offer a systematic and objective snapshot of a specific point in time. And these techniques are usually ideal for the early stages of scientific investigation, especially when researchers are simply trying to determine whether a specific mental activity or behavior exists in the real world. So for instance, if you wanted to answer a basic question like what specific study techniques do high school students actually believe are the most effective, a descriptive approach gives you the baseline reality check. So within this approach, three major techniques exist. We have observational studies, self-reports, and the deeply detailed case study. So a case study is an intensive, hyper-focused deep dive into a single individual or a small group of highly unique people. And the primary benefit of a case study is the sheer volume of rich, very detailed information that you are able to collect from one subject. All right. So much of what we know about human neuroscience comes from very bizarre historical case studies. Take the famous case of the patient known in scientific literature as N.A., who suffered a tragic freak accident involving a miniature fencing foil that pierced his brain through his nose. And following the injury, they developed severe amnesia and lost the ability to form most types of new long-term memories. By conducting thorough long-term case studies on this individual, cognitive psychologists mapped out the exact neural regions responsible for memory formation, proving that damage to specific brain structures selectively disrupts how we store our daily experiences. However, case studies do carry one massive drawback, and that is their findings are not always, in fact, they're almost always not generalizable to the rest of, people, right? So it's one case, right? There's, and this happens a lot as well in the scientific community where this happened with this one person or this small group of people, and we think that that means that's how all the people that fall into this category are going to act and react and so on and so forth to things. It is not remotely accurate, all right? Are there some things that are case studies result in a lot of other experiments and studies that go on that may yield results for generalizability later down the road, but in most cases, right, you can't look at one case study of one thing and be like, yeah, that's how it is for everybody. It just doesn't work that way. Okay, so observational studies, they involve systematically assessing and coding observable behavior across time intervals. So instead of bringing people into an artificial laboratory, researchers observe subjects in their real-world environments. And so to keep things objective, researchers use a process called coding, which means breaking down chaotic actions into predefined categories, like counting how many times the subject smiles or raises their hand or glances at a phone screen during a 10-minute window. This technique is famous thanks to legendary primatologist Jane Goodall, who spent years silently watching chimpanzees in Tanzania, and by systematically recording their daily interactions, she proved that chimps forge complex social bonds, use tools, and display distinct personalities, establishing observational research as the ultimate baseline for discovering what's actually happening in a brand new field. However, playing the ultimate invisible spectator comes with two major scientific obstacles that can totally disrupt the data. The first big hurdle is observer bias. This occurs whenever a researcher's own background, cultural assumptions, or personal expectations influence how they interpret and code the behaviors that they see. Imagine a scientist watching two people scowl during a heated debate. If the researcher holds a subconscious belief that men show anger while women show distress, they might code a man's facial expression as being aggressive and the exact same facial expression on the woman as being sadness. The researcher is not necessarily lying, it's just their brain filtering information through the lens that they already have. The second major obstacle is reactivity, often called the Hawthorne effect. Reactivity happens when living subjects alter their natural behavior simply because they know they are being watched. Whether it is a wild chimpanzee acting cautious because Jane Goodall is sitting nearby with a notebook and they're like, what the heck is this human doing here? Or a high school student acting like a total angel because the principal comes in to observe the classroom and they're usually chaotic and trying to make people sniff their armpits and stuff like that, right? So I taught all freshmen and freshman boys are a lot. So anyway, I don't know why they constantly touch each other either. Didn't do that as a freshman boy myself, but nonetheless. So when researchers need to gather massive amounts of information about what people think, feel, or do, they often turn to self-reports. It's a descriptive research method where participants directly provide information about themselves. And the most common forms of self-reports are surveys and questionnaires, which are structured sets of written questions. So these tools are incredible because they are fast, cheap, and can gather data from thousands of students in a single afternoon. If a researcher wants to go deeper and ask more detailed follow-up questions, they might conduct a face-to-face interview instead. However, self-reports carry a major flaw known as self-report bias. Whenever a participant does not answer completely honestly, often tweaking their responses to match what is considered socially acceptable or to make themselves look smarter, cooler, or nicer than what they actually are. So in sociology and psychology, this is closely linked to the social desirability bias, our hardwired human desire to present the best possible version of ourselves to other people. If a survey asks how many hours you spend studying versus how many hours you spend playing video games over the weekend, you might feel a subconscious urge to inflate your study hours so that you don't look lazy. To combat this issue, researchers must design neutral questions and strictly guarantee that all responses remain anonymous and confidential. So if you ask the question, what study techniques do students believe are best? A case study will not work because we need insights from hundreds of students and not just one person. An observational study falls short because watching someone sit at a library desk doesn't really tell us what mental strategy they're using. The best approach in this case would be self-reporting. So when psychologists surveyed real students, they found a staggering 78% believed that passive rereading was one of their most effective study methods. But here's the ultimate takeaway. A self-report often only reveals what people think is true about their behavior and is not always the reality. So when psychologists want to move past simply describing behavior and start predicting future outcomes, they turn to correlational methods. So the ultimate goal of this research design is prediction. So correlation means that two variables are mathematically or systematically related to each other in the real world. And unlike controlled laboratory experiments, researchers do not manipulate anything here. Instead, they measure two variables as they naturally occur in the wild and examine whether a reliable pattern exists between the two things. This makes correlational design an essential weapon in the psychological toolkit when manipulating human behavior directly would be unethical or physically impossible. Correlations generally move in two distinct directions, positive or negative. A positive correlation means that as one variable increases, the second variable also increases. For example, psychological studies have repeatedly identified a positive correlation between total time spent scrolling through social media feeds and self-reported feelings of depression. So, as screen time ticks upward, reported depressed systems tend to climb right along with it. However, it's essential to remember that even if two variables move together in perfect sync, that positive relationship alone does not mean one factor automatically causes the other. On the flip side, a negative correlation means that as one variable goes up, the other variable goes down. Think of it like an inverse relationship in a video game economy. As your time spent hanging out in person with close friends goes up, your feelings of social loneliness tend to plummet down. One variable rises, the other one drops. So now let us apply this to our ongoing question about student learning. Is there a measurable relationship between the time spent using a specific study technique and the final exam performance? So to test this without alerting anyone's study schedule, researchers survey students to record how many hours they naturally spend on their preferred strategy, like rereading a textbook chapter versus taking active retrieval practice quizzes, and then cross-reference those hours with their actual test grades. So when researchers analyze the data, they often discover zero correlation between hours spent passively rereading and final exam scores, and rereading for 10 hours produces virtually the same results as rereading for an hour, but they consistently find a strong positive correlation between hours spent on active practice quizzing and higher exam grades. Because this positive correlation exists, scientists then can make a reliable prediction that a student who commits more time to self-quizzing is statistically far more likely to end up at the top of the academic leaderboard whenever the grades are finally posted. Okay, so correlational research doesn't establish causality, and it cannot determine if one factor causes another. The directionality problem arises because the relationship isn't really clear, and this is when two variables are correlated. A standard survey cannot tell you which direction the causal arrow is actually pointing. Consider the well-documented correlation between heavy social media usage and depression. Does spending 6 hours scrolling curated video feeds cause a teenager to develop depressive symptoms, or does an individual who is already feeling depressed naturally isolate themselves in the bedroom and scroll on the phone far more often? A correlation simply reveals that two factors walk hand in hand. Cannot tell you what the variable is driving the bus and which one is just along for the ride. Right? The second hurdle is the third variable problem. Often completely hidden and unmeasured factors, a sneaky third variable operating in the background, is the actual cause behind the observed factors. And returning to our shark and ice cream paradox here, I'll skip that one. So because correlational methods excel at prediction, which is one of the four main goals of psychology, a strong correlation exists between severe clinical depression and increased suicide risks. And even if a correlation alone cannot map out every single biological or environmental trigger, that reliable connection allows clinicians to make life-saving predictions and intervene whenever a patient is at high risk. Okay, so while observational studies and correlations allow for us to discover patterns and make clever predictions, experimental methods are the absolute gold standard in psychology. They are the only research design that can definitively establish cause and effect. And so instead of sitting back and watching variables naturally drift together, a researcher steps into the lab like a game developer and systematically manipulates one specific condition while keeping everything else perfectly still. This gives us the power to move past simple co-occurrences and state with absolute certainty that factor A directly causes the change in B. So to map this cause and effect relationship, scientists divide their focus between two critical components, the independent variable and the dependent variable. So return to our ongoing study on academic performance, where we want to test the hypothesis that active self-quizzing leads to better exam scores than rereading. And the independent variable is the condition that the researcher intentionally manipulates or changes, and so it represents the hypothetical cause in the experiment, and its values are entirely under the scientist's control. And in our study, this is the assigned study technique. And on the flip side sits the dependent variable, which is the specific behavior score or outcome that the researcher measures as a result of that changes as a result of the manipulation or doesn't. It's called the dependent variable because it is the final numerical value, literally depending on how the independent variable was altered. In our learning experiment, the dependent variable is the student's final percentage score on the exam. Understanding this dynamic is crucial for dissecting psychological science, and the independent variable is the input tweak you test, while the dependent variable is the output stat that you are going to measure. So to ensure a psychological experiment is genuinely scientific, researchers cannot rely on fuzzy, open-ended concepts. They have to create operational definitions which specify the exact procedures used to qualify, meaning describe, and quantify, meaning measure, every single variable in the study. Think of an operational definition as the ultimate step-by-step strategy guide or craft recipe in Minecraft. If you do not list the exact quantities and specific ingredients required, no one else can replicate your item, and your build completely falls apart. So let us apply this to our independent variable, the assigned study technique. You cannot just tell one group of students to go study and the other group to go quiz themselves. All right, you must operationally define the exact parameters before collecting any of the data. So for the passive reading group, you must lock down the specifics. How many times will you read the text? Are they allowed to use a yellow highlighter? Do they get 20 minutes or an hour? And for the practice quizzing group, you must define the exact mechanics. How many flashcard questions can they answer? Are they multiple choice or fill in the blank? Do they get instant feedback on wrong answers? And setting these strict rules ahead of time guarantees that you are manipulating the variable in a very clear, consistent, and unbiased way across every single participant. Next, you need a precise operational definition for your dependent variable, the exam performance. Terrible, highly subjective definition would be asking students on a scale of 1 to 10 how they feel about how they mastered the material, because human self-perception is notoriously unreliable. A strong, objective operational definition would measure the exact percentage of questions answered correctly on a standardized 30-item test administered immediately after the study session. And establishing transparent operational definitions is crucial because it keeps a scientist completely honest, preventing anyone from altering the rules of the study halfway through in order to force a desired result. More importantly, it provides a flawless, crystal clear blueprint that allows for independent researchers around the globe to replicate this same experiment down to the exact detail. When other scientists can run your exact recipe and produce identical results, your findings earn rock-solid credibility within the scientific community as a result. We're almost there. Sorry, some of these first ones are the longest. So, when psychologists run an experiment to prove cause and effect, they cannot simply give a single group of people a new treatment. Instead, what you have to do to prove that your independent variable, the factor you're intentionally changing, actually caused a measurable shift in the dependent variable, you have to compare your results against a standard benchmark. So scientists accomplish this by randomly splitting their participants into at least two distinct conditions, the control group and the experimental group. The control group serves as the baseline comparison, and participants assigned to the control group do not receive the special treatment, active manipulation, or experimental intervention that is being tested. Instead, they experience standard neutral or placebo conditions, and in our ongoing study on academic performance, the control group consists of students instructed to use traditional, repeated reading of their study material, and this group establishes the baseline test scores expected under normal everyday study habits, giving researchers a crucial benchmark to measure real progress. On the other side of the laboratory sits the experimental group. This is the group that actually receives the specific manipulation, special treatment, or new condition that is under investigation. In our learning experiment, the experimental group consists of the students assigned to use active, repeated practice quizzing by directly comparing the final exam scores of the experimental group against the baseline group of the baseline scores of the control group. Researchers can mathematically determine if the active quizzing technique created a genuine measurable improvement in their learning. Beyond showing performance differences, the structured experimental design completely solves the directionality problem that plagues conventional studies. And in correlational research, you never know which variable came first, like trying to figure out whether playing competitive video games increases stress or if stressed out people simply play more competitive video games. But in a controlled experiment, the researcher directly manipulates the independent variable before measuring the dependent variable, and because the study techniques were systematically altered at the start, scientists control the exact chronological timeline, and this clear sequence allows the psychologist to eliminate guesswork and confidently prove that the specific study method was the direct cause of the higher exam scores. So, have you ever spent a ton of time grinding to unlock a rare, high-tier weapon in your favorite multiplayer video game, only to get completely crushed in your very first match because your opponent was running a game-breaking glitch? It's an absolutely infuriating feeling because you have no way of knowing if they actually played better than you or if the hidden glitch stole your victory from beneath your grasp. In experimental psychology, running into an unmeasured glitch that ruins your results is known as encountering a confound. A confound is an unwanted outside variable other than the independent variable that you're trying to test that accidentally affects the outcome of your experiment. Confounds act like sneaky imposters in your data, creating an alternative explanation for why things happened and rendering your final conclusions completely meaningless. So to establish a true cause and effect relationship, your independent variable and dependent variable, an experiment relies heavily on rigorous control, and in scientific terms, control means the researcher takes active, deliberate steps to ensure that every single factor remains identical between the experimental group and the control group, isolated down to the one variable being tested. Consider what happens when control breaks down, or when the control completely breaks down in our ongoing study habits experiment. Right? So imagine assigned research set up a test to prove that active self-quizzing beats passive rereading, but during the design phase, the researchers accidentally made a huge mistake. They give the experimental self-quizzing group a short, super easy reading passage about basic pop culture, while giving the control rereading group a dense, extremely difficult passage on quantum physics. When the final exam score comes back, the self-quizzing group completely dominates the test, but can the researchers actually claim that the active self-quizzing group is the superior study method? Absolutely not, because the hidden difficulty of the reading material acted as a major confound. So the researchers don't have a way of knowing whether the students scored higher because of their study technique or simply because their reading passage was 10 times easier. So to fix that and preserve the integrity of the science, the researchers must exert strict experimental control by keeping every environment condition very consistent. All right, so to understand how scientists stretch their findings to fit millions of real humans, we have to unpack two fundamental concepts: the population and the sample. The population represents the entire mega group of people you want to learn about, such as every single high school student in the entire country or every active Genshin Impact player on the planet. Obviously, testing millions of teenagers individually would take endless amounts of money and an eternity of time. That is where samples come in. Instead, a sample is a smaller, manageable subset of the larger population that researchers actually bring into the laboratory to study. Think of it like taking a single spoonful of ramen broth out of a giant boiling pot. If the spoonful is mixed properly, the tiny taste tells you exactly how the whole pot tastes without forcing you to chug the whole bowl at once. Right? So to make sure that the tiny spoonful gives an accurate preview of the whole pot, researchers aim for the representative sample using random sampling. In a true random sample, every single individual in the target population has an equal unbiased probability of being selected for the experiment, and it operates like a perfectly coded random number generator or a fair gotcha pool where no single account gets unfair favoritism. If you put every high schooler student ID in the nation into a giant digital hat and pulled out 1,000 names at random, your sample would naturally balance out different ages, backgrounds, and personality types. However, executing a pure random sample in the real world is almost impossible due to budget limits and logistical nightmares. Because of this, scientists frequently rely on a convenient sample, which simply consists of people who are easily accessible, like college freshmen attending a researcher's own university. While convenient sampling saves huge amounts of time and effort, it carries a massive catch to it. The results might not translate to different groups, such as teenagers in rural communities or students in another country, and that's why psychologists must continually replicate their studies using diverse samples. And when multiple independent experiments across different cultures and age groups yields identical results, researchers gain rock-solid confidence that their conclusions are genuinely universal.